So let me start defining the metric space. Metric spaces. So first we will define what do we mean by a metric, and then we will define the metric space. So it's a definition a metric on a set omega is a mapping D which takes elements from this Cartesian product. So like this D will take two elements of this omega and they will throw them on 0 to plus infinity real numbers, and it has to satisfy. So metric on set omega is a mapping satisfying the following three conditions. The following three conditions. So condition number one is the definiteness. So definiteness means if the distance, or so when I say distance I mean metric. So if this map is applied on x and y, it is 0 if and only if x and y is same point or the same element. And the second property is the second property is obviously the symmetry. And symmetry means if you are taking the distance between x and y, it is same as distance between y and x. And the third is the triangular inequality. So we say triangle inequality, and this triangle inequality is this: if you are taking the metric between x and y, then this is less than equal to this metric between x z plus. Okay, so now I think now I'm audible, right? See, so I will repeat this, otherwise you'll find them in the video, I'm sure. So what is a metric? So a metric is a map on this product space. So in other words, what I'm saying is the distance, the metric is the map that will take two elements from this set and will assign them a non-negative real number. So additionally, this map D is going to be metric if it is going to satisfy three axioms. First is the definiteness. So it says that if the distance between, or metric between two elements is 0, then the elements are same. And if you are taking second is the symmetry. So that means if you are taking the metric between x and y, and then y and x, so it has to be same. And the last axiom is if you are taking distance between, or metric between x and y, it has to be less than x and z, and then y and z. So let's without wasting time, let me start doing an example. So here is an example, some of the examples of the metric spaces. So the first simple example that I will take is let's say this is any set, so omega is a set, and I'm defining the distance between x and y is 0 if x is y, and it is 1 if x is not y. Now you can check the first example. If the distance between x and y is 0, this piecewise function gives you x is equal to y. And if x is equal to y, then this piecewise function gives you this distance of this metric is 0. And the second is, if you are taking the distance of x and y, so it is going to be 0 if x is y and 1 if x is not y. So you just change the order, so take this y this side and x this side, y this side and x this side, so you will have this distance yx. So that's not a big deal. Additionally, the third one is this, so I think there will be cases for this, so I'm leaving this for you, xz plus yz. So you have to satisfy that this one is also satisfied, right? So we will check this, and this metric is called discrete metric. Discrete metric. One more thing, when I have defined the metric on a set, so for example omega is a set and you found a metric on it, so now this will become a metric space. So a metric space is nothing but it's a set on which you have defined a metric. So you are taking, if you are taking any set and you are defining a metric on it, then the set will be a metric space. I'll take another example which is non-trivial, and then we will be talking about the other side, which is the normed spaces. So let me now say, so let's take this omega. So omega is this guy, 0 to plus infinity, and plus infinity is included here. Okay, and the distance or the metric is defined by this 1 upon 1 plus x minus 1 upon 1 plus y for all x, y inside this 0 to plus infinity. So now your task is to show that this is indeed a metric space. So this is a metric space and this is a metric. So we will verify that this satisfies the three axioms. And the first one is to say that, let's check this. If the metric is 0, then 1 upon 1 plus x minus 1 upon 1 plus y is 0. And this will give you 1 upon 1 plus x equal to 1 upon 1 plus y. And that will again give you x plus 1 equal to y plus 1, which will give you x equal to y. And I think you can proceed backward as well. So like if you assume x equal to y and then you add 1 on both sides, and then you can start and reach to this destination, this is not a big deal. So you will do this. Second is this one, distance between x and y. So this is 1 upon 1 plus x minus 1 upon 1 plus y. Now if I take distance between y and x, distance between y and x, what is going to be this 1 upon 1 plus y minus 1 upon 1 plus x. Are these equal now? So yeah, like there will be a mod. Yeah, so there is a mod. I missed this. There is a mod. So this is a mod, right? Okay, this is okay. Fine. I was also thinking why there is a problem. Yeah, so there is a mod. Okay, it's perfectly fine now. Now this is fine. Now these are equal, so just take minus as common and you will get this distance between x and y is same as distance between y and x. The next and the we might start with this. चलें. If we start distance between x and y, this is 1 upon 1 plus x minus 1 upon 1 plus y. Then I can write 1 upon 1 plus x minus 1 upon 1 plus z, and then plus 1 upon 1 plus z minus 1 upon 1 plus y, and all of this mod. अच्छा, अब इसको एक कंसीडर करें और इसको एक कंसीडर करें, and then apply the triangle inequality for the mod absolute. So 1 upon 1 plus x minus 1 upon 1 plus z plus 1 upon 1 plus z minus 1 upon 1 plus y. Now this guy is the distance between x and z, and this guy is the distance between y and z, and this is greater than or equal to distance between x and y. So that is shown, right? So in this way, this space 0 to plus infinity with this D is a metric space, right?